Greetings, AP Chemistry students. Today we're going to start the second part of Unit 7, which is solubility and KSP. And before we get too far into that, there are some terms that we need to define. So the first term is dissolution or solvation. This is the process by which a solute breaks apart and associates with a solvent. For the purposes of this unit, we're essentially talking about ionic compounds. So it's the process by which you break the ionic bonds within a compound and then you form ion dipole interactions with the solvent, which is usually water. A saturated solution is one in which you cannot dissolve any more solute. You could have an unsaturated solution where you could dissolve more, and then there's also special cases called supersaturated where you've dissolved more than typically done by manipulating the temperature. But in a saturated solution, you cannot dissolve any more solute. A key way to identify the presence of a saturated solution is if you have excess solute just sitting in the bottom of the container as a solid. For instance, if you dump a bunch of sugar into some water and you stir it up and you still have sugar sitting in the bottom of the container, just sitting in the bottom of that sugar water mixture, that's a saturated solution. You can't dissolve any more. The excess is sitting in the bottom of the container. Now, solubility is your equilibrium position for this process. And what's called the molar solubility is the value of X in your ice chart if you were to make an ice chart for this process. So, those are your key terms that you need to know in order to understand what we're going to be doing in this unit. Now, KSP is the solubility product constant for a saturated solution. Now, a KSP is written the same way as any other equilibrium expression. And just remember that we don't include solids in our equilibrium expressions. So, for instance, the compound iron 3 hydroxide has a KSP of 4 times 10 to the negative 38th. Now, iron 3 hydroxide, it will dissolve to make iron 3 ions and 3 hydroxide ions. And our KSP expression equals the concentration of iron times the concentration of hydroxide cubed because it makes 3 hydroxide ions when it dissolves. So now we could ask ourselves, what is the molar solubility of iron 3 hydroxide at 25 degrees Celsius? So to solve this problem, we need to set up an ice chart. Now, since iron 3 hydroxide is a solid that we're dissolving and these other things are aqueous, the solute does not appear in here in the expression. We also don't include the water. Water is a pure liquid, so it's also left out. Now, before any iron 3 hydroxide has dissolved, these initial values are 0. Now, on the change line, the iron 3 will go up by x, the hydroxide will go up by 3x, so that at equilibrium we have x and we have 3x. We then plug into our KSP expression because KSP equals Fe plus 3 times hydroxide cubed. So 4 times 10 to the negative 38th equals x times 3x cubed, which equals 3x cubed is 27x cubed times x is 27x to the fourth. So to solve for x, we need to take 4 times 10 to the negative 38th, divide it by 27, and then take the fourth root of it, or raise it to the 1/4 power, if you will. And the answer I'm coming up with is uh, essentially 2 times 10 to the negative tenth. So the molar solubility of iron 3 hydroxide is 2 times 10 to the negative 10th molarity. That is the molar solubility. It's how many moles of iron 3 hydroxide will dissolve in a liter of water. It's also our Fe plus 3 concentration, and the hydroxide concentration would be triple that value. So that's how you would do a simple calculation like this. So let's look at another problem. Bismuth sulfide has a molar solubility of 1 times 10 to the negative 15th moles per liter. Calculate the KSP. So for this, we need to set up an ice chart where Bi2S3 will dissolve to make 2 bismuth ions plus 3 sulfide ions. These would be aqueous. This is a solid, of course. You set up an ice chart. These start at 0 before any of it dissolves. This goes up by 2x. This goes up by 3x. So at equilibrium, we have 2x and 3x. Our KSP equals the concentration of bismuth squared times the concentration of sulfide cubed. So our KSP equals 2x squared times 3x cubed, which that's going to be 27 times 4, which is 108 x to the 5th. Well, the other thing is that this molar solubility, well, that's x. So all we have to do is put in to our calculator 108 times 1 times 10 to the negative 15th to the 5th power. And I'm getting 1.08 times 10 to the negative 73rd. And KSPs, again, are unitless by convention, so do not try to put units on this. So I hope this is a little helpful. I do want to remind you of a couple of little things that are important to remember with saturated solutions. So first of all, as long as there is solid remaining in the bottom of the container, your solution is still saturated. And the other thing is that KSP, as with all chemical equilibria conditions, depends on temperature. If you're not told the temperature, you assume you're at 25 degrees Celsius for all problems in AP chemistry. There are charts of KSPs in various textbooks and internet resources. Most of them are given at 25 degrees Celsius. But you may know, for instance, from making sweet tea, for instance, you can increase the solubility of sugar in water by heating it up. And then you add the sugar and then you make a super saturated solution. But we're not going to be considering those for our equilibrium calculations. We're just going to be talking about saturated solutions, and you can make a more saturated solution by increasing the temperature, and it would cause more to dissolve in most cases. So, hope that helps. I hope y'all have a wonderful day.